Well, hey everyone, and welcome back. I'm starting what will be a small mini-series, sort of, that'll be maybe 4 or 5 videos, just on the layers of the Earth. While I've been doing mostly, in my previous series that's been titled The Basics of Geology, I've been covering mostly applied geology, or stuff that you would actually do on maps, or diagrams, etc. But in this video I'd like to cover just some very basic theoretical stuff. So we're starting off with the layers of the Earth, and the top layer, the crust. So just a brief review, if you aren't aware, the Earth is divided into layers that have different chemical and physical properties. So we have the inner core, which is in the very center, which for now we'll just call that a very hot sphere of metal. There are many other things to talk about with the inner core, but we're trying to be brief as far as this video goes, because it's mostly focused on the crust. The outer core is a spherical shell that surrounds the inner core. It's responsible for generating our magnetic field. The mantle is a thick, semi-solid, sort of plasticky layer that's constantly in motion and is responsible for the motion of our tectonic plates. And finally, the outermost layer we have here, the crust. And kind of like with the crust of bread, you may notice that on this diagram of the Earth, although it's not by any means exact, the crust appears incredibly thin, and that's true to the actual Earth itself, because I'll start writing some facts down here. The crust accounts for 1% of the total Earth's volume. So when you think of all of the rocks that we know, all the tectonic activity that occurs, plates in motion, strata that we may map out on cross-sectional diagrams, when we think of anything, for example, mines, anything that has to do with being below the Earth's surface is always within the crust. We never really get to mapping out any piece of the mantle or getting down there to investigate anything. This hard silicate layer that essentially composes the geosphere of the Earth is only 1% of the Earth's total volume. I find that to be incredibly amazing. Just something to think about. Now there are 2 types of crust to sort of differentiate, and they're incredibly simple. Continental and oceanic. And if you couldn't figure out what those mean, continental is the crust that we stand on, that you're most likely standing on right now, the crust that composes the land masses, and oceanic crust is the crust that forms the ocean floors. Now a few facts about them. Continental crust is mostly granitic, coming from the word granite, granitic in composition. Oceanic, on the other hand, is basaltic, coming from the word basalt. Hopefully those sound familiar if you're familiar with rocks and minerals. So granitic is continental, basaltic is ocean. Those are just their compositions in general. Continental crust is usually thicker than oceanic crust. Although crust in general is incredibly thin and a very small piece of the Earth's volume, continental crust is usually between roughly 30 through 50 kilometers thick. Some sources may tell you it's more between 35 and 45. Doesn't really matter too much. 30 through 50 is a good amount, I think. While oceanic crust is usually only 5 through 10 kilometers thick. So continental crust is thicker, and additionally continental crust is older. It's about, on average, if we were to average all of the continental crust, going from the youngest meaning the strata that's deposited right at the surface, down to the very bottom where it makes its contact with the mantle. The continental crust is on average 2.0 billion years old. Meanwhile, the oceanic crust is significantly younger, actually 10 times younger, at an average of 200 million years old. Okay? And finally, continental crust is almost always less dense than oceanic crust, a lower density, meaning a lower mass to volume ratio. So essentially that means if you were to take a chunk, let's say maybe about a cubic meter of continental crust, you know, a big old chunk, and you were to put it on a scale and then put an oceanic crust, the same amount of oceanic crust on that same scale, it would tip, you know, the oceanic scale, the oceanic crust, the chunk of oceanic crust would weigh more because though it was the same volume, oceanic crust has more mass per unit volume, and therefore the same volume of oceanic crust will be heavier than continental crust. So with these differences, one of the ways to remember it is that as a person, I would find continental crust more, oceanic crust more appealing because it's thinner, younger, and more dense. More dense, you know, muscle is more dense than fat, so we would describe that as being more muscular rather than flabby, which continental crust appears to be maybe like a sort of a large old woman, not to offend anyone. And then granitic and basaltic, those aren't facts you really need to be too aware of, but just know that their compositions are different, and that actually allows us to differentiate them in a way, on a level beyond just, well, oceanic crust is found on the ocean floor and continental crust is found on continents, right? Simple as that. And just a few more facts coming your way as far as the crust goes. And those are related to temperature. As you would expect, as you get deeper and deeper into the crust, increases temperature. Go figure, because there's heat radiating from the Earth's core. And because of that, the deeper you go into the crust, the hotter it'll get. The surface is cold, and most of the heat it receives is from the sun, the amount of the sun's energy that is radiated through the atmosphere. However, as you get deeper and deeper into the Earth's core, the Earth's crust, you'll go from it initially getting colder because you're below the surface and not receiving much of the sun's energy, to all of a sudden it starts getting hotter because you're getting closer to the thick, semi-solid, warm mantle. Warm is probably an inappropriate word in this case. The very hot, too hot for humans to survive mantle. So to tie an actual number to this, for every 1 kilometer you travel downwards, on average it increases about 30 degrees Celsius. And if you're like me and you're from the US, and you don't like to think of things in Celsius but rather Fahrenheit, 30 degrees Celsius is a pretty significant temperature change. It's not like 30 degrees Fahrenheit where it doesn't make that big of a difference. Well, I suppose 30 degrees Fahrenheit actually is pretty big of a difference, but, 60 degrees is quite a bit warmer than 30 degrees, and 90 degrees is hot, while 60 would be warm or cool depending on how you like your temperature. But that's a complete tangent. Just know that a change of 30 degrees Celsius is pretty significant. And that's on average. Once you get even closer to the contact between the crust and the mantle, it gets this gradient increases even more. And speaking of the contact between the crust and the mantle, at the mantle, meaning at the contact between the crust and the mantle, the crust is somewhere between 200 and 400 degrees Celsius in temperature. So yeah, the crust at the bottom of it, once you get through the 30 through 50 or 5 through 10 kilometers between you and the mantle, it's going to be pretty hot, and that's why humans have never dug to the mantle. I'm sure you can imagine that these temperatures are not very comfortable at all for us. And with that, that's pretty much all I wanted to talk about, just some simple facts. So basically, just remember the crust. Solid, thin, and cold. These two, of course, are relative to the rest of the Earth. Obviously, 50 kilometers at most is by no means a thin measurement, and 400 degrees Celsius is by no means a cold temperature. However, when you've got the core of the Earth getting up to almost 2,000 degrees Celsius, yeah, there's no comparison really. So solid, thin, and cold. Remember that for the crust. It's our outermost solid, thin, cold layer.